Good afternoon and welcome to another video. Today we're going to learn about universal gravitation and Kepler's laws. So this is about what gravity is, how it works, and specifically what the motions of the planets are and what the rules that govern them are. So what are we going to do? We're going to learn about the history of the study of gravity, some fundamental properties of gravity. We're going to introduce the law of universal gravitation, talk about the universal gravitational constant. We're going to model some situations involving gravitation, learn Kepler's laws, and learn about circular orbits and escape velocity. First of all, what is gravity? We all have sort of an idea of what gravity is in our day-to-day lives. We know that we feel the force of gravity from the Earth that holds us onto the ground. If we drop objects, they are moved by the force of gravity. But what is it really? Well, gravity, by definition, is a field force which acts at a distance. We do have some forces, like the normal force and friction, that require contact between two objects, normal force being perpendicular to the surfaces and friction being parallel. But gravity does not need to have contact with another object to exert a force. All objects with mass exert a gravitational force on all other objects. So we think of gravity typically as from the Earth on us, but everything with mass exerts gravity on everything else with mass. You have a gravitational attraction to your phone. You have a gravitational attraction to your desk or anything else. We can also draw field lines to illustrate a gravitational field and what it looks like if we were to visualize it. So a gravitational field, we have field lines. So imagining that this point right here is the Earth, if we were going to back up, take a zoomed out picture and illustrate the gravitational field as vectors, the force vectors that are pointing towards the Earth. So any object out here is going to be experiencing a force of gravity from the Earth that points radially inwards. So any object out here is going to be experiencing some gravitational force that is pointing directly radially towards the Earth. So let's look at this picture of the Earth and the Moon. So interestingly, we end up with sort of not exactly a dead spot, but in between the Earth and the Moon, there is this area where the gravitational attraction from the Moon and the Earth are equal. So obviously the Moon has mass. We know that we can have astronauts stand on the Moon. Hooray. But we also have people that can hang out on the Earth. When you get close enough to the Moon, the gravitational attraction of the Moon is greater than the gravitational attraction of the Earth, so you can stand on the Moon. But right in this area, there is one particular point where the gravity from the Earth and the gravity from the Moon are equal. So you could kind of just hang out in this area without accelerating towards the Earth or the Moon, but it is a very, very small point. But the interesting thing to notice is that we have these field lines coming in this way. So if you were to approach from somewhere out here, you would experience a gravitational attraction along this kind of path because you are being affected by both the Moon and the Earth at the same time. The history of gravity. We all have this idea, this folktale, I suppose, about Isaac Newton and the apple falling on his head, and he wonders about, oh, how did this apple fall? And boom, there was the discovery of gravity. But it's a little bit more complicated than that. It actually involved some deep thoughts about the Moon and what the Moon was doing. So he started with this thought of, yes, he understands. So we all know that an apple starts up here, ends up on the ground. It falls some path. It actually falls straight down. But Isaac Newton was thinking, okay, well, we know that objects fall towards the Earth. There is some force that is acting that is causing these objects to come down. Well, I can also see the Moon. If this apple is, 1 meter above me, the Moon I can see must be many, many thousands of meters above me, but it is also above me. And should there not also be some force that is pulling the moon towards the Earth? So why does the moon not fall directly into the Earth and crash into us? Well, what he came up with was that the moon is, in fact, in free fall under the force of gravity, right? So free fall we describe as when something is just accelerating towards the Earth, is what we usually say, and that it is under no other forces except for gravity, maybe air resistance, but true free fall is when you're under only the influence of gravity. Well, he figured that the moon is indeed falling, in quotes, free fall, but that it is not crashing into the Earth because it has some velocity. So because the moon is moving relative to the Earth, it is still experiencing the force of gravity, but it's not actually crashing, quote unquote, crashing or falling in a straight line into the Earth. So how does this make sense? Well, let's look at the moon's orbit. We know that the moon follows a semi-circular, or very close to circular orbit around the Earth. And we can tell that, obviously, we know that the acceleration or the force from the Earth has to be pointing towards, because if we have a person standing here, we have always drawn our force vectors of the force of gravity straight down. And it turns out, if you put another person over here, that arrow also goes straight down. So all of these vectors point straight towards the center of the Earth, and this is true for the moon. The force, so the force of gravity from the Earth on the moon, does point straight towards the center of the Earth. Why does it not fall? Because the moon already has velocity. So we look over here, this is our velocity vector. At this instant in time, the linear velocity of the moon is pointing completely perpendicular, is that right angle, to a line that connects the center of the moon to the center of the Earth. Why is this significant? Well, it's significant because at this instant in time, the force of gravity is trying to pull the velocity, or pull the moon, and change its velocity vector this way. What does that look like? Well, if we imagine the next instant in time, here is the moon again. Say now it's over here. Well, the acceleration due to gravity has pulled, quote unquote, pulled the moon, and now its velocity vector, if we take this vector and we add a little tiny bit of this vector, we end up with this as our resultant vector. So we know how that we're adding vectors. One is going this way, one is going this way. The sum of those vectors points in this direction, right? So this vector, this little green vector right here, is now the linear velocity of the moon, and it just so happens, well, it doesn't just so happen, the math works out that it is still perfectly tangential, meaning we have a right angle, to a line connecting the center of the moon to the center of the Earth. So at the next instant in time, so if this is here's our current velocity vector, well, guess what? The force of gravity is still pointing straight towards the Earth. And what is that going to do? It's going to, here's our force vector, and then if we add those vectors together, we add, there it is. So at the next instant in time, so now the moon, say, is over here, our velocity vector, our green vector from over there, now points this way, and it is still perfectly at right angles. So we keep doing this over and over and over again, and every time we have some tangential velocity that is perfectly perpendicular, and our force still points directly towards the Earth. So indeed, the moon is in free fall. It is, quote unquote, falling towards the Earth, but because it already has some velocity, the force only changes the direction of that velocity. So that is how we end up with an orbit. Okay. From this, Newton put 2 and 2 together and took a little bit of a few steps worth of math, a little bit of complex algebra, a little bit of calculus. Newton famously was the inventor or discoverer. It's kind of an argument whether you can invent or discover math, but of calculus. But he ended up with this. This is the law of universal gravitation, right? The force of gravity on mass 1 and the force of gravity on mass 2. Now, these are indeed an action-reaction Newton's third law pair. Talk a lot about Newton. So we would say that if this was the vector, it would be from 2 on 1, and this would be from 1 on 2. Nonetheless, they are equal in magnitude. And what is the magnitude of that force? Well, it turns out it is the mass of the first object, that's in blue, is the mass of the first object, the mass of the second object, multiplied together, and then the radius, this r, is squared. What is this r? It is the distance from the center of mass of one object to the center of mass of the other object. And that's an important distinction. When we have objects that are very large, if you were comparing two planets, then we would have to make sure that we were not using this distance, but instead we're using this distance between their centers of mass. And finally, what is this last piece? We have a capital G. What is this? This is called the universal gravitational constant. It is a constant determined by experiment that makes sure that these numbers match up. So if you multiply these masses in kilograms, divide it by the radius squared in meters, you need to multiply it by this universal gravitational constant to get the force in newtons. It just makes the units work out properly and everything matches up appropriately. So, talk about Newton's third law. We said that these two forces, force 1 and force 2, so force 1 on 2 and 2 on 1, those are an action-reaction Newton's third law pair. Each object involved in the gravitational attraction receives the same force, okay? The same force. You exert as much force on the Earth as the Earth exerts on you. The acceleration is different. So the same force, we're using Newton's second law, sum of forces equals mass times acceleration. So if we receive the same force, if the Earth has a much, much higher mass than we do, which it does, then its acceleration is going to be very small, and we will see that in a moment. But each object is, again, in free fall towards the other object. That's our definition of free fall, is under the influence of gravity from one object to another. So when you jump, you are falling towards the Earth, but by definition, the Earth is also falling towards you because you are exerting a gravitational force on it. So let's talk about the center of mass. When we talk about gravity, we say that the force is coming from, so from what to what? It's coming from the center of mass of one object, and it acts on the center of mass of another object. Okay, so we go back to our spheres. Okay, here's our two spheres. Here are their centers of mass. The force is coming from, or acts from, one onto the other. And we know that it acts on the center of mass because that's how we draw our free body diagrams. We always draw the forces acting at the center of mass. But we can also say that the force is being exerted from the center of mass of another object. For large objects like stars and planets, they are usually spherically symmetrical. That means that they are spheres, perfect spheres that are circular on all axes. So there's a circle here, and there's a circle around the median, and a circle around the circumference. so they are of uniform density as well, generally. So their centers of mass end up at what we would expect them to be, the geometric center of that sphere. So it works out kind of nicely. We don't have weird, oval-shaped planets or rectangle planets or things like that. It does not happen. Generally, if we're talking about galaxies, yeah, we have some ovals going on. But for planets and stars, nice round spheres, pretty much. So the universal gravitational constant G. It's a very interesting number. It's come up by experiment. It appears to be just one of the fundamental concepts of the universe. There are these constants, these numbers. There's things like pi, there's things like E, and there's big G, and there's some other constants. So when I say big G generally when I talk about gravity. So if I say big G, that's what I mean, is the universal gravitational constant. So these numbers just kind of pop up in nature. It seems that they are inherent to nature. Regardless, it can be determined through experiment by actually measuring the force applied and then measuring the two masses and the radius appropriately. You can just calculate G. It would be the slope of a graph of r squared, or mm over r squared, and force. That would give you a slope of G. For you math nerds, I am one of them. And that has a value, an experimental value. This is the generally accepted, most accurate value of big G, 6.67, etc., times 10 to the negative 11, very, very small, meters cubed over kilogram second squared. So those are the units that make mass, radius squared come out to force in newtons, and that's just what the number is. So we're going to talk about two 100 kilogram asteroids, and we are going to say that they are 1,000 meters apart. So let's just find out what the force between them is. Super simple math. If we're going to find the force from one to the other, this is a gravitational force. We're going to say big G. What are we going to start with? We're going to start with big G, m1, m2 over r squared. Okay, what do we end up with? Force of gravity 1 on 2 equals 6.67 times 10 to the minus 11th times 1,000 kilos, 1,000 kilos. Okay, we have mass 1 is 1,000, and mass 2 is 1,000, so that's here and here. We put those right into our formula. All over 1,000 meters is our radius squared. So lucky for us, if we break this up, we have 6.67 times 10 to the negative 11th. And then if we're looking over here, it turns out we have 1,000, 1,000, break up the square, 1,000, 1,000, and these cancel. So at the end of the day, what did we get? We saw that the force of gravity from 1 on 2, and therefore, by Newton's third, the force of gravity from 2 on 1 is equal to 6.67 times 10 to the negative 11th newtons, right? So we got to make sure that we include our units when we get to the end of this. And let's just make an interesting point here. This is a very small number. Minus 10 to the 11th is a very, very small number. The forces that we experience in our day-to-day lives are generally on the order of, 1 to 100 or maybe 1,000 newtons in our day-to-day lives. 10 to the negative 11th, very, very, very small. So in terms of like as far as forces go, gravity tends to be it's a weaker force. It seems to be very weak in the grand scheme of things compared to the other forces that we experience day to day. The reason that gravity seems so massive or so inescapable on Earth is because we're not dealing with 1,000 kilos. We're dealing with a lot more when we talk about the Earth, a lot more mass. So here's an important distinction that needs to be clarified: mass versus weight. So mass and weight are kind of thought of as the same thing, and they're absolutely not. So when we talk about mass, it's how much you have of something. It doesn't change no matter where you are, okay? You have the same mass on Earth, on the sun, out in space, on Jupiter. The same mass is there because it is a measure of how much you have. It is a certain number of atoms. If I have 5 kilos of aluminum, there are an exact number of atoms of aluminum that are in that 5 kilos. No matter where I go, there are always the same number of atoms in that kilo. Weight, however, is a measure of the gravitational force being exerted. The weight is a measure of the gravitational force, and that changes. If you are a 5 kilo mass on Earth, it's very different than being a 5 kilo mass on Jupiter because the gravitational force from Earth and from Jupiter are very different. So weight can change quite a bit. Weight is measured in newtons. Mass is measured in kilos. Important distinction: mass and weight are not the same thing. Mass does not change. Weight does change because weight is a measure of gravity. Quick test. Let's use the law of universal gravitation here on Earth, right? So we're just going to test it. We're going to see if we get anywhere close to our expected, what we use generally, the acceleration due to gravity. We expect that we would end up with 10 meters per second squared. So let's see if we get anywhere close to that, right? So we're going to use F equals gmm over r squared. So here's what we're going to do. We're going to say this is for a person. So from the Earth onto a person, force of gravity is big G, 6.67 times 10 to the negative 11th. Mass 1, we're going to say that this is the mass of a person, 80 kilos. Mass 2, we're going to say is the mass of the Earth. Remember when I said that we're dealing with a lot bigger than 1,000 kilos? The mass of the Earth is 6 times 10 to the 24th kilos. That's a lot. That's a lot of mass. Okay. And then for our radius, if we think about drawing a picture, here's the Earth. Here's our tiny little person. The center of mass of the Earth is at the center. So the radius of the Earth from the center to the surface is around 6.4 times 10 to the 6th meters. And if we zoom in, here's our person. And the center of mass of the person is actually kind of in the center of your body, sort of in your chest, closer to your hips than to your head. But that is such a small distance, half a meter, if that it's not going to make any amount of difference on this value. So we're just going to use the radius of the Earth. So we'll throw that in there, the radius of the Earth. That is right here. I'm going to say it's 6.4 times 10 to the 6th. And that's squared. So now we can do some math. We'll do some real quick math. Force of gravity, Earth on person equals. All right, let's do math. I can totally. 6.67 times. So we end up with, we have 320.16 is the numeral times 10 to the, so we have plus 10 to the 14th. And if we do that under here, 40.96 times 10 to the 12. Okay, so if we do this, divided by 40.96 equals 7.816 times 10 to the second. Okay, so we doing our powers of 10 here, 14 and 12. We end up with 2, a difference of 2. So we end up with the force of gravity from the Earth on the person is equal to 781.6 newtons. Okay, so that's the force of gravity, right? But what were we looking for? We wanted to find the acceleration due to gravity. So this is the force that's being exerted on a person, right? So Earth on person is 780 some odd newtons. So if we're going to find the acceleration due to gravity, we have to use Newton's second law, and we end up with 781 newtons equals the mass of 80 kilos times the acceleration. And if we do this out, we end up with approximately 9.76 meters per second squared. And that's real good. That's real darn close considering how rough of numbers we used. We assumed that we only use one significant digit when we talk about the mass of the Earth and only 2 when we talked about the radius of the Earth. But we got really close. We're using 10 meters per second squared generally, but the accepted value is actually a lot closer to 9.8 meters per second squared. So we did pretty darn well. So we can see that the law of universal gravitation, at least in this context, works. Hooray! Now, just for kicks, let's do this. So we know that the force of gravity from the Earth on the person is equal to 781.6 newtons, which is also equal to the force of gravity from the person on the Earth. So let's do a little Newton second. 781.6 newtons equals mass of the Earth, which if we look way back up there is 6 times 10 to the 24th kilos times the acceleration. And if we do a real quick thing here, we get 130 times 10 to the negative 24th meters per second squared is the acceleration. So what do we get? We got around 1.3 times 10 to the negative 22nd meters per second squared is the acceleration of the Earth due to our gravitational force. So the gravitational force that you exert on Earth causes an acceleration of 1.3 times 10 to the negative 22nd meters per second squared. So that's why we don't exactly see the Earth rushing up to greet us when we jump. Here's a little bit of a harder example. So we have two spheres of equal mass, one with radius r and one with radius big R and one with radius little r. They're touching at their surfaces. What is the gravitational force from one to the other? We are going to say that they are of equal mass m. And this isn't a terribly complicated example, but here's what we're going to do. It requires us to remember some important things about gravity. So let's say that we have these two spheres. One is radius big R, one is mass little r, and they are both mass m. So what do we want to do? We want to find the gravitational force. So we're going to leave big G as big G. So we're going to find the force. We're going to find force of gravity from 1 on 2. Let's say if this is 1, this is 2. Equals, we're going to leave big G as big G. There it is. What are we going to do next? Well, we're going to take the masses. We have mass and mass. Good so far. And here's the snag. What radius are we going to use? Oh no! If we were thinking about two objects that are really far away from each other, if there's an object over here, an object over here, well, clearly it is this distance, right? The center of masses are far away enough from each other that we can kind of, whatever, it doesn't matter. But this time it does matter. What are we really looking for? We are looking for the distance between the center of mass of one object and the center of mass of the other object. So we can quite clearly see that that distance is going to be big R plus little r. So if we're going to write that down, that would come out to be big R plus little r all squared. Okay, pretty straightforward. You can leave it like that, but the point of this example is that the radius, right, the distance between the center of masses of the two objects. So even though these are touching, they still exert gravitational force on one another, and we need to use this distance, which is the distance between their center of masses. So, Kepler's laws, what are they? They are laws that govern or describe the motion of elliptical orbits. So we'll talk about ellipses in a second, but Johann Kepler in the 1600s, this was way back, analyzed patterns that he and Tycho Brahe observed in the orbits of the planets around the sun. This was before high-powered telescopes, or if memory serves, even any legitimate telescopes at all. They would just look up and they knew where the planets were, and they took very, very careful data, and they came up with these laws, which are very, very accurate, even, way back in the 1600s. Real smart guys. They developed 3 laws that are true for all the planets in our solar system, and with some modifications, they are true for all orbits, period. Just no matter what. This is how orbits work. We're talking about things orbiting other things due to gravity. Fun fact, Tycho Brahe had a pet moose. So what is Kepler's first law? This is called the law of orbits. So what he says is all planets move in elliptical orbits with the sun at one focal point. Okay, so an ellipse is basically a stretched out circle. You take a circle, pull it that way, you pull it that way, and we end up with an ellipse. Hooray! Now we know that a circle has one point that is equidistant, right, is the same radius all the way around. In an ellipse, this is not the case. Not true for ellipses. What we have are, instead of one center, we have 2 focal points. And if you are trying to draw an ellipse, you need these 2 focal points, right? The further away they are from each other, the more elliptical or the more stretched out it will become. If they move closer together until they are one point, then you have a circle, right? So the sun is one of these focal points that determines how the ellipse is going to look. The other focal point is kind of just hanging out in space. It's not a legitimate object. It is just a point. But because the sun is so massive and the gravitational force, we end up with elliptical orbits. So here's our planet. We have 2 important points. The perihelion, that is here. That is the point at which the planet is closest to the sun. And we have aphelion. Aphelion is when we are farthest from the sun. So if our planet is moving along, it gets here. Now it is really, really close to the sun, this distance. And then our planet is moving along. Now it's here. It has this very much longer distance from the sun. Those are the definitions, those two things. So what do the orbits of the planets actually look like? Well, it turns out they look pretty darn circular, most of them. So the letter E, we say that E here, we call it the eccentricity. So eccentricity is how elongated an ellipse is. So an eccentricity of 0 is a circle, and the larger the value is, the more elliptical it gets, or the more elongated it gets. And it approaches 1. So you start off with, here's a circle that has an E of 0. Then you get larger ellipses and even more stretched out ellipses. And then eventually you get these crazy long ellipses. And if you ever hit an eccentricity of 1, that is just a line. Just a line, not even a circle anymore. So you can't really have an eccentricity of 1. But if we look at Earth, its eccentricity is very low. It's 0.017. So it's pretty darn close to 0. But still, if we're looking at, if this is the sun, the dotted line would be where the perfect circle orbit is. So if this dotted line, so we can see that the Earth deviates from that just a teensy tiny bit. Mercury, quite a bit. That has a larger eccentricity. So compared to the dotted line, the actual orbit of Mercury is definitely more elliptical. Mars, bigger than Earth, but not terribly big. We see again, we have this dotted line is what it would look like if it was a circular orbit around the sun. So we do have a little bit of an ellipse going on. So most of the planets they do have elliptical orbits, but they're not crazy elliptical. They're pretty close to circular, but not perfect. What's Kepler's second law? It's called the law of areas. This one's a little bit odd, but we're going to try to understand it. So what does this mean? A line connecting the planet to the sun sweeps out equal areas in equal time. So this has interesting consequences. What does it mean? That means that as a planet goes along in its orbit, it's moving along like this. This line right here, line from the planet to the sun, as it moves along, that line sweeps out a certain area. Okay, so if we were to measure the area of this wedge, not exactly a triangle, it's more of it's a wedge, that would have a certain area as a, just a polygon. What Kepler's second law says is that if this area is the same value as this area, then it took the same amount of time, this delta t and this delta t, it took the same amount of time to move this distance and this distance. And that turns out to be true. It was one of his postulates. He formulated this from data, but it turns out to be true, that the area swept out by a line connecting the planet to the sun must be the same for the same time. So, consequence of this, if we have moved linearly, if we were to draw a line, just close to a straight line right here, and a straight line right here, we see that we would move a much shorter distance over here. So if we were going to go a linear distance, is a shorter distance over here, and then over here it is a longer distance. What does this mean? That means that the velocity of a planet as it orbits the sun is non-constant. So planets are moving at a non-constant velocity as they orbit. So it has to be going faster. So the velocity here has to be faster than the velocity over here, right? So if I was going to write this out, it'd be like, here's v1, v2. So v1 would have to be greater, v1 would have to be less than v2 because it has less ground to cover, less distance to cover in the same time, because these must be the same time. This also means that we have greater angular velocity over here, but we haven't talked about angular velocity yet. So linear velocity is all we have to care about right now. Linear velocity is all we have to care about. So the third law, the law of periods. So the period is the time that it takes for a planet to orbit the sun. So for us, we call that 1 Earth year, and that has a direct connection to the major axis of the ellipse, which is the distance from the center to the perihelion or the aphelion. So if this is the center here, our major axis is this distance, or alternatively, this distance. Okay, so if we were to take the long part, right, we'd measure the long part, the diameter through the long part is what is called our major axis. So there's a direct connection. What is that connection? The square of the period, here in red, of any planet is proportional to the cube of the major axis. Where is that? That is right here. A is the major axis. T is the period. Here it is. It crops up again. Gravity, big G, universal gravitational constant, pops up here. And if we're talking about planets, M is the mass of the sun. Yeah, that is right there. So we can see that there is a constant of proportionality in 4 pi squared, but we can see that proportion-wise, it comes out to the period squared is proportional to the major axis cubed. Proof of this? So this is actually a plot of the period squared against the major axis cubed, and it ends up that we do get a slope of 4 pi big GM. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Obviously, these are getting further away from the sun as we go, and the period that it takes to get all the way around the sun is progressively longer. So Pluto takes the most time to go all the way around the sun, and Mercury takes the least time. We can see that when we get up to, just as a curious thing, when we get up to Uranus, we end up at about, the square of the orbital period is around 10,000. That means we take the square root of 10,000. If I'm not an idiot with math, I think that's 100 years-ish. So that means that we end up with a 100-year period for Mercury. And Pluto's even longer than that. If my math is wrong, it's probably wrong. Okay. Circular orbit. So circular orbit, this is when you have an eccentricity of 0. And this does not happen in reality. However, we can model it, sort of. When the masses that you're dealing with get too disproportionate, then you end up with something that is super, super, super close to a circular orbit. The eccentricity is 0. So if we're going to say eccentricity is 0, let's draw our circle here. If this was an ellipse, it would be the distance from the center of the ellipse to the perihelion or the aphelion. So in this case, it's just the radius because it doesn't matter. There is no difference. So for an ellipse, there's a difference between this distance and this distance, but not so in a circle. So we can just, instead of A, we can put in R cubed. That's the radius of that circle. Radius of the orbit, so distance from the surface of the planet or the Earth or whatever, if we're talking about a satellite. We can find the speed from the law of periods, right? We can find the speed that an object has, right? So if we're going to draw, here's the Earth, and we have a satellite out here following some path, some circular path, if I can draw to save my life. Some semicircular path. Here's our satellite. It's got little wings or whatever. it has some particular speed that it is maintaining constant all the way around the Earth. How can we figure that out? Well, we know that we need to end up with meters per second. So let's use that as a guiding tool. What are we going to start with? We're going to start with period squared equals 4 pi squared r cubed over gm. What's our next step? Well, let's think. We have t is in seconds. This is meters cubed. This is kilos. So over here we have seconds squared. We have meters cubed. All right, let's try to rearrange that. So if we put t squared over, for the sake of argument here, we'll have 4 pi r. Let's take it squared. Okay, equals r over gm. Well, what do we have? Now we're going to compare units. Now we have seconds squared over, our units are meters squared. And then we have meters over a whole bunch of gobbledygook that we don't necessarily care about. But look what we have over here. We have seconds squared over meters squared. Looks good. Let's flip it so we might be able to get meters per second. So we flip it around, we get 4 pi r squared over t squared equals gm over r. And here's a piece that we can look at. Let's take the square root. So if we take the square root of all of this, 2 pi, this should have been squared, right? Pi squared, my apologies. So we have 2 pi r over t equals root gm over r. What is 2 pi r? So 2 pi r is the circumference. So we end up with circumference over the period, right? And we said the period is the time that it takes to go around once. So it ends up that we have the circumference over the time per revolution. We have the circumference over the time that it takes to get all the way around the circumference. And that is exactly meters per second, our velocity. What did we end up with? So we get, as a final result, the velocity of an object. So here's our, again, let's go back. Here's our Earth. Here's our Earth. Here's our satellite. Pretty little wings. So the velocity of our satellite as it orbits around the Earth at some particular distance, r, remember this is an r, not a v, ends up being the square root of big G, universal gravitational constant, mass of the Earth, over r, and that is the distance from the center of mass to the satellite. Real quick to this, kind of pivoting away just to make the distinction. So we talk about, when you think about rockets, you hear this thing called escape velocity. Escape velocity. So escape velocity is different than orbital velocity. What we just did was orbital velocity. This is the speed that something that is in a constant orbit has as it circles around. This orbital velocity, right? Well, an escape velocity is how fast you would have to basically shoot something tangential to the Earth's surface for it to escape the gravitational field of the planet entirely. So there is a certain speed that you would have to go. It turns out, we remember from our orbital velocity is big G, root of big G m over r. Our escape velocity is 2 times big GM over all R all under a square root. And we just want to make the distinction that it is different than the orbital velocity. If you launch something at orbital velocity, it will continue to orbit, nice and pretty. If you launch something at escape velocity, it will leave the planet's gravity forever. So when we talk about rockets, rockets don't actually need to attain escape velocity at their launching, because they have propulsion systems attached which are continuously accelerating while it's going up through the atmosphere. So when you launch a rocket, you don't just give it some initial speed and then let it do its thing. You're continuously accelerating that rocket through the atmosphere. Escape velocity is only something that applies when you're launching an object from the surface of a planet with no further acceleration and no air resistance. So if we had the Earth and there was no air and we wanted to get something away, that would be from right on the surface, we would need to use the escape velocity. But rockets don't work that way. They have rockets. Final takeaways from all of this. I know it's been a long video, but what are we going to remember at the end of all this? All objects with mass exert a gravitational force on all other objects with mass. So the Earth exerts a force of gravity on you. You exert a force of gravity on the Earth. You exert a force of gravity on your phone. The table exerts a force of gravity on you. The magnitude of that gravitational force is given by this formula. The force is big G times the mass of the two objects over r squared. G is the universal gravitational constant. It is a constant of nature. It is determined through experiment, and it has a value of approximately 6.67 times 10 to the negative 11th meter cubed per kilogram second squared. And we learned a little bit about Kepler's laws. Kepler's laws govern the motion of planets. They move in elliptical orbits. The velocity of a planet as it goes around in its elliptical orbit is non-constant. And that's pretty much all we have at this point. So gravity, it's more complicated than you thought, but still very interesting. Thank you for bearing with me. Make sure that if this is still timely, if you're not watching this to review or you're not watching it late, please go into the description and take the quiz. If I gave you a handout, which I should have, please complete the open response question. Bring that in. See you in class.